This is lesson 3.4, combining transformations of functions. The focus of this lesson will be how to apply translations and stretches to the graphs and equations of functions. So basically what we're doing is we're compiling everything that we've learned in lesson 3.1 to 3.3 and putting it all together. So we might be moving it left, right, stretching and pressing in both the vertical and horizontal direction. First thing I want to look at with you is how the order in which transformations are applied may make a difference to the final outcome. So if we take a look at the graph on the left-hand side here, what we'll see is that we start with a translation of 2 units down, and then we're going to follow that by a vertical stretch of factor 3. And then on the right-hand side, we're going to switch the order. We're going to do the vertical stretch first, and then the translation 2 units down. So if we look at our regular graph right here of y equals x cubed, that's this graph right here, the first thing that we're going to do is we're going to translate it 2 units down. So if you take a look, every ordered pair has just been moved down 2. So this ordered pair at 0, 0 is now at 0, negative 2, and so forth. This ordered pair over here at 1, 1 has been moved down right to here. Okay, so then we get this new equation. The new equation is y is equal to x cubed minus 2. And then from there, what we're going to do, right, is we're going to stretch it by a factor of 3. And we get this new equation, right? So this one right here. Okay, and then that's the new equation like so. Well, what has happened? Well, this ordered pair that we'd moved down to 0, negative 2, we take that negative 2 value and we multiply it by a factor of 3, and we have it now at 0, negative 6. Okay, this ordered pair right here that was at 1 and 1, notice that these are going up by halves at a time. This ordered pair at 1, 1 right here has been moved down 2 right to here, and then it's at negative 1, so we multiply that negative 1 by a factor of 3, and it's now here at negative 3. Okay, so again, that was when we moved it 2 units down to start, and then we did a stretch of factor 3. So what would happen if we moseyed on over to the other side here and we looked at what would happen after a stretch of factor 3? And then we did the 2 units down. So this ordered pair at 0, 0, for instance, so this is my y is equal to x cubed right here. What would happen if we multiplied it by a factor of 3? Well, that ordered pair at 0, 0 obviously doesn't change. This ordered pair right here that was at 1, 1 would now be at 1, 3. Okay, the same thing as this ordered pair that's at negative 1 right here would now be at negative 3. And then what we're going to do is then we move that graph, so it's this one right here, if I kind of trace over it, that graph is going to then go down 2. And so we have something that looks like this. And you can see that the final outcome, this graph right here versus the final outcome over here, definitely looks different. Okay, so we have to be careful in this lesson that we kind of follow our order of operations when we're dealing with the transformations of functions. All right, so let's go and deal with example 1 right here. Example 1 says, here's the graph of y is equal to g of x. Sketch and label its graph after a vertical compression by a factor of 1/3, then a translation of 2 units up. So first, let's go deal with the vertical compression by a factor of 1/3. So that function would look like the following. We'd have y is equal to 1/3 g of x. All right, so basically all the x values will stay the same, but the y values are going to get multiplied by a third. So if we take a look at this point right here, that's has a y coordinate of 3, it's now going to be right down here at positive 1. All right, this value right here that's at negative 3 is going to be at negative 1. This value here of 0, 0 times 1/3 just stays the same, and this one at 6 is now at 2. Okay, and then in pink right here, what I'll do is we'll graph the other function. So we have y is equal to 1/3 g of x, and now what we're going to do in the pink here is going to have 1/3 g of x, and then we have to go a translation of 2 units up. So all of these green values that we just had here are just going to move 2 units up. So we just do one of these transformations at a time, like so, and like so. And you can see that we would now have the following function right here. Okay, so we just follow in the same order that we're given, that we have right here. I like to graph my one transformation at a time and then deal with the second one. Okay, let's go on to the next page. So in general, what we can say about combining stretches, compressions, and translations is we have the format that you have seen before, like so. And each one of these things is going to do something different. So if we focus on our value of b right here, remember what b is going to do. That's going to give you your horizontal stretch or compression right here, and that's of the reciprocal of the absolute value. And then we know if b is less than 0, it's going to be a reflection. The vertical stretches or compressions happen according to a right here. And then, of course, if a is less than 0, then that's when the graph is going to get reflected, this time in the x-axis. Okay, and so after you've done that, then we go and we take a look at our translations. So we have a horizontal translation of h units. So remember, like if you saw x minus 2, we'd actually move it in the positive direction 2 right there. And then the vertical translation of k units right here. So if you saw y plus 3 like so, it's actually going to move the graph 3 units up. Okay, and so in general what we can say is we know that the ordered pairs are going to look like the following if we combine everything. And so this is very important. This our x coordinate after all our transformations is going to be x over b plus h, and the y coordinate is going to be ay plus k. Okay, so this part right here would be something that is probably worthwhile to know quite well, because it'll make the next examples, which are a little bit more complicated, a number of different transformations, a little bit easier. Okay, so in general, I've given you a little bit of a note right here. Note when graphing from an equation, to ensure the correct transformation image is sketched, apply the transformations this order. So just like we said right there, we're going to deal with your stretching and compressing first, the reflections, and then left, right, up, and down your translations. Okay, so let's take a look at example 2 right here. Example 2 says, here's the graph of y is equal to f of x. Sketch the graph of y plus 4 is equal to f of 1/2 of x plus 1. Okay, and then after we've done that, they want you to state the domain and range for our original function, so the functions that is labeled right here, and the new function. So just to remind you of the format that we've learned, I'll write it right here, maybe in this blue color. We have y minus k is equal to a f of b of x minus h, like so. And so each one of these letters, k, a, b, and h, is going to do something slightly different with our function. Okay, and so the first thing I want to do is I want to note what these values are for these four variables. First thing that I see is that let's deal with our k value. So if I have a positive 4 in here, it actually means we have a negative 4, so that's going to move my graph down 4. My a value, I can't see any a value, so we assume it's a 1. The b, of course, is 1/2. And finally the h, because it's a plus 1, we do the opposite value, make it a negative 1. Okay, so what I'm going to set up here, and what I would encourage you to always do, is make kind of a little bit of a hybrid table of values right here. Because what we're going to do is we're going to look at the original function. We're going to take some of these known values that we have, and then what we're going to do is we're going to apply the different transformations to those ordered pairs, and then we can graph our new function. Okay, so on the left-hand side here, I'm going to have y is equal to f of x. So that's the function that I'm given. And on the other side right here, I'm going to have our new function after a number of different transformations. Just like so. Okay, so in general, I'm going to be looking at the ordered pair xy right here, and so let's take a look at the possible ordered pairs that I have. So what do I see right here? I see I have, we'll work kind of from the left to the right. I have an ordered pair at -2 and -0.5. I have an ordered pair at -1, -1, and then almost the same values, but just positive 1, 1, and 2, and 0.5. Okay. All right, so now that we've done that, let's take a look at how this transformation is going to affect my given ordered pairs. So let's start with x. All right, the x coordinate right here. Well, because the horizontal value that we have here for b is 1/2, I know that it's going to multiply my x value by a factor of 2. So I'm going to have 2x, and then I see right here that I'm moving the graph horizontally in the -1 direction, like so. All right, and then what's going on in the y part? Well, I don't have a value for a, so that means it's not going to be stretched or compressed vertically. Remember, this one was the horizontal, so I know that I just have y right there. And then I have a k value of -4, so that means the graph is going to go down 4. Okay, so in general now, this makes it so much easier for us. Now we can just take these regular ordered pairs that we have right here, substitute them into this little hybrid ordered pair that we've made, and you will have the ordered pairs for your new function. Okay, so we would have the following. If we go -2 times 2, that's -4. -4 minus 1 is -5. If we put in -0.5 right here, -0.5 minus 4 is -4.5. And if we continue in the same fashion, you will have the following. -3, -5. 1, -3, and then finally 3 and -3.5. So again, how do I get those values? I'm just substituting them into that function. Okay, so let's graph these. I have 1, 2, 3, 4, 5, so -5, and then -1, 2, 3, 4, 4.5. Okay, so that's my first order pair. I have another one at -3, 1, 2, 3, and -5, which would be approximately right here. I have another one at 1 and -3, so 1, 2, 3, and then one at 1, 2, 3, and then down 1, 2, 3 and a half. Okay, so in general, what you can do as well for these functions, notice how this one has these asymptotes running right here and right here, is you can just take a look at how the asymptotes would have been moved. So since this graph went down 4, this asymptote that was at y equals 0 is now going to be at 1, 2, 3, -4. So if you want, that might make it a little bit easier for you. And this asymptote that was at x equals 0, it's been moved over 1 in the positive direction. Sorry, I should say in the negative direction. So we will have our asymptote like so. And so in general, what can we say about this function? Well, we can see that this function is going to look approximately like so when we graph it. Okay. And the last thing that we needed to do for this is we need to talk about our domain and range. So let's extend this little table right here, and we'll just turn this into my domain and my range. Well, my original function right here, what could we see? Well, my original function, we didn't have any x or y values at 0. So we'd say that x cannot equal 0 and y cannot equal 0. And now, because we've moved our asymptotes a little bit, we would say that x cannot equal, in this case, because we moved it over 1, it'd be at -1. And the range, we have every possible y value up and down that we could possibly have, with the exception that we can't have anything at this value of -4. So y cannot equal -4. So to summarize what you do in general for these is I would start by figuring out what your 4 different variables are. And then the big thing is you need to figure out these ordered pairs right here and how those ordered pairs are going to be moved. Make your first table and then just use those ordered pairs to give the various transformations. Okay, let's look at example number 3. So example 3 says use the graph of y is equal to the square root of x to graph y minus 2 is equal to negative the square root of 3x plus 3. Then again, just like we did before, state the domain and range. So the first thing I will do right here is get you to write the equations. We have y minus 2 is equal to negative the square root of 3x plus 3. And you'll notice that this is not in the format that we're used to right here, because normally we have our b value and then brackets x minus h. So what we're going to do in order to change it and put it into that format is we can simply just factor the leading coefficient from our 2 terms right here. So notice that this becomes 3 and then x plus 1. All right, so now we can explicitly see what our h value is going to be. So let's go just like we did before and let's write those known values over here on the side. So we have k, we have a, b, and h. And so if we take a look, my k value is going to be positive 2. Right? We do the opposite of what you see right here. My h value right here is going to be negative 1. The b value that we have in front is going to be 3. So we'll have a horizontal compression. And then finally, the a value, we do not have an a value with the exception of this negative, which means we're going to have a vertical reflection across the x-axis. So this will be a negative 1. Okay, and so just like we did before, let's start by making this table of values. So the table of values that we have, we start with our original function, that is y is equal to the square root of x. Our new function is y minus 2 is equal to negative the square root of 3x plus 3. Okay, I like to go and define my ordered pairs first. So this ordered pair obviously is just the same, x, y. Let's go and figure out what we're going to do to one of these things. So because we have a b value of 3 right here, that means that we're going to have a horizontal compression of 1/3. So that means I'm going to start by multiplying my x variable by 1/3. And then if we take a look in our brackets right here, this was going to move us 1 in the negative direction. So we'd have 1/3 x minus 1 for my x coordinate. The y coordinate is a little bit easier. The a value is going to cause it to be reflected, a vertical reflection like that. And then we're simply, my k value was 2, so that means that the graph is going to be translated 2 units up. Okay, so now that we have that written, let's go and take a look at some of the known ordered pairs that we have. We have an ordered pair right here at 0, 0. We have an ordered pair, it looks like at, well, we know actually, because this is the function y is equal to the square root of x. You can't really see it right here, but we know for a fact that we would have the ordered pair 1, 1. We know for a fact that we would have the ordered pair 4, 2, and indeed you can see that 4, 2 would be right here. Notice that this side is going up by increments of 2, where this is going up by increments of 1. Okay, now let's apply these transformations. So if we put 0 in here, 1/3 times 0 minus 1 gives me a negative 1. If we put in 0 right here, negative 0 plus 2 is just 2, so we have the first order pair, negative 1, 2. If we put in 1 right here, we have 1/3 times 1 is 1/3. Minus 1 is going to give me negative 2/3. So that'll be tough to graph, but we can estimate it. And then if we put in 1 for the y, we have negative 1 plus 2 is 1. And lastly, if we put in 4, we have 4 times 1/3 is 4/3. 4/3 minus 1 is going to give me 1/3. And if we put in 2 right here, negative 2 plus 2 gives me 0. Okay, so let's sketch what this thing is going to look like. I'll do it in pink right here. So this first order pair that was at 0, 0 is now going to be at negative 1. So negative 1 would be, remember because these are going over by increments of 2, negative 1, 2 would be approximately right here. All right, negative 2/3 is going to be pretty tough to do right here, but it's at negative 2/3 and 1, approximately like so. All right, we have 1/3 and 0 is going to be something like that. And if you see, it's kind of tough to figure out what the function is going to look like. My guess is it's going to go something down like this. We might even want to do an extra ordered pair. Now the interesting thing is this ordered pair is technically on here. Notice how this is going over by 2's. We have another ordered pair that you could fit on here, this ordered pair at 9 and then at 3, because the square root of 9 is 3. So we might want to put another one on there. So we have 9, 3, and then we know that if you put 1/3 of 9, that gives you 3, and 3 minus 1 is 2. And then if we put in 3 right here, we have negative 3 plus 2 is negative 1. So that might help us a little bit, just give us a better idea of what's going on. So we then have another ordered pair here at 2, negative 1, like so. Okay, so in general, the graph is going to look something like so. Okay, and again, this is just a sketch. All right. Finally, let's talk about our domain and range. So we'll extend the table of values here. All right, D for domain and R for range. How about my original function? Well, my original function right here, it looks like we have x values that are greater than 0, so we'd say that x is greater than 0. Same for y. All right, and then let's take a look at what we know for the domain. Well, the domain, what's the most negative value that we have right here? Well, we have it at negative 1. Remember, these are going over by increments of 2. So this, we would say x must be greater than or equal to negative 1. The highest value we have in the y direction is at 2, and then it's going infinitely down. So we say that y must be less than or equal to 2. All right. Last but not least, we have example number 4 here. Example 4. The graph of y is equal to g of x is the image of the graph y is equal to f of x after a combination of transformations. Corresponding points are labeled. Write then verify an equation for the image graph in terms of the function f. So what you see right here is we have function y is equal to f of x, which I'm just trying to kind of lightly outline in green right here. And then we have our new function, which has been transformed in a number of different ways. Okay, and so this is going backwards, where you are actually going to have to come up with the equation rather than coming up with the sketch like you've done before. I think the most valuable thing to do right here is to first write the format that we're going to have to put our new function into, and that's y minus k is equal to a of f of b of x minus h right here. Okay, and so what we're going to do is we're going to try to figure out, of course, what all our different values are right here. Okay, so let's first start right here with b. Let's figure out if we have anything going on in terms of a horizontal stretch or compression. Well, what I notice right here is if we take b, so this is the original graph b, and we see how b prime has changed. You'll notice that the difference between that point right there and this point right here is 2 units. And then if you compare this point right here, which would have its corresponding point right here, it also has a difference of 2. And so what we can see is that there has been no horizontal stretch or compression. So because there's, I'll just make note, no horizontal stretch / compression, therefore what we can say is we know that b is going to equal 1 right there. Okay, so nothing's really changed. Next value I'd like you to take a look at, also to deal with x right here, is h. Quite obviously you can notice that this b point has been moved over 2 right there. So you might want to just make a little note here like we did before. Point b, as an example, has been moved 2 to the left. So therefore, what can we say about h? We can say that h is equal to negative 2. Okay, so those are the first things that we need to figure out. Next, let's go and attack what's going on with our a value. Okay, so the easiest thing to take a look at with our a value is what type of a distance did we have in our original function between a and b. So if you look at a right here, it's at a point at 8, and b is down here at 2, 4, 6, negative 8 as well. So the distance between a and b, just vertically right here, was 16 units. And if you look at a prime to b prime, it is now 8 units. So we know that it's been halved. All right, so vertical distance has been halved, and so then what we can say is we know that a is going to be equal to 1/2, like so. Okay. So finally, if we focus on k right here, what you can simply see is you can see that the difference between a and a prime is that the values of our a value has been halved, and then it's now 4 units down after that has happened. So if you were to take this 8 value right here and half it, you get to a value of 4, because remember we knew that our a value is equal to 1/2 right there, and then we'd still have to go down 4 to get to that a prime right there. And so what we can say is after a vertical compression of 1/2, a prime is still 4 units down from a. And so then in general, just like we've said before with all these ones, we can pretty confidently say that k is equal to -4. Okay, and so in general then we have our function would now be y plus 4, because we had a k value of -4 right there, is equal to 1/2. That was my a value. F of, we did not have a b value, so I'm just not even going to write it right there. It would technically be 1. And then we have x with my h value of plus 2, like so. Okay, and so so that would be our function. So that concludes this lesson. We've taken a look at how you can be given a function with multiple transformations and graph it, or how we can kind of go backwards where you're given the graph and then you come up with the equation, much like we did right here. All right, that concludes this lesson.